Hi, my name is Arash and I'm today presenting my project on model-free reinforcement learning with self-active critique control for residential HVAC energy management. As for the motivation and problem setup, residential heat pumps support decarbonization, but they can increase winter peak loads. Supervisory control under time of use pricing must balance these comfort and cost. Model predictive control, as one of the most popular advanced control strategies, performs well, but it requires accurate physics-based model of the building itself. So our goal here is to use model-free deep reinforcement learning. Here we're using soft Actor-Critic for heat pump control in a high-fidelity simulator called Ocker. As for the Ocker is a testbed for residential energy management simulation studies. And here we are focusing on a single family house, which is modeled with Ocker Gym, which is basically a gym environment built on top of Ockers itself. Our system is a single input, single output one. We have indoor air temperature state, thermostat set point action. Our air source heat pump provides space heating during a cold winter week, which is the first week of February. Here we also have a strong external forcing from time of use price and outdoor temperature. The right bottom figure shows the evolution of outdoor temperature for the first week of February, and the left bottom figure shows the off-peak and on-peak electricity prices for one whole day. As for the soft-acted critic agent and baseline control methodology, we have state action reward. As for this other problem, we are using enough policy soft-acted critique, which basically has replay buffers, many batch updates, and automatic entropy tuning. As for the baseline, we are using a rule-based controller RBC with a fixed 21.5 degrees Celsius temperature set point, which basically this ignores time of use pricing. For the training convergence, we are using it training horizon of January. The whole month has 31 days with 30-minute time steps. For the horizon or look ahead, we are using 12 hours of forecast for weather and prices. We have around 150,000 time steps, which equals to 100 episodes for this specific problem. And we can see from the below figure that returns improve rapidly, and after some time it gets stable. And after 60 episodes almost, we are reaching to an optimal policy for this RL problem. So this slide basically shows the learn preheating strategy and the final result. So evaluation is done on the first week of February under the same time of use tariff. Our soft-active critic agent slightly raises the set point before noon, basically. For all days, we can see the set point is increased. And after that, during the peak window, it lowers the set point basically and lets the temperature drift within the comfort band. And we can see that the temperature goes up to the lower comfort band. Here, the reason that it comes up is basically not to violate the occupant thermal comfort. So the blue line shows lower comfort level, and the green and the red dashed line basically shows the upper comfort level. As for the baseline thermostat, it holds a constant set point and keeps running during expensive hours. We can see that the black dash line is the set point of the baseline, and the solid black line is the set point of the RL controller. And we can see that the evolution of the indoor temperature is basically according to those set points. So we can see that the RL basically is using less energy compared to baseline. So we have done 7-day test period with identical weather and price signals for both RBC and RL controllers. Our baseline or RBC incurs a total energy cost of $845, and our RL agent basically incurs a total cost of $696. It basically means that our RL agent has been able to save 17.4% of energy costs compared to our RBC algorithm. And in terms of the occupant discomfort, the discomfort level for RL is basically negligible. It's only 0.12 degree hours for RL, and we are within the thermal comfort bands. So we are concluding our talk here. We have been able to develop this model-free RL agent and save 17.55% of cost savings compared to an RBC model. And for the future work, we will be focusing on cooling strategies and field deployment and things like that. Thank you very much for your attention.